Hey there, class. Mr. Prusky here. Hope you're having a good day so far. We're continuing with Chapter 2. Chapter 2 is kind of about reasoning, okay? So it's about proofs and logic and kind of the core. Basically, everything we can do in math is because someone proved that, like, 2 plus 2 is 4 in all situations, okay? So that's kind of what we're doing. So our first lesson today is called Use Inductive Reasoning. And the essential question is, what are some strategies to recognize patterns in math? And math is all about patterns. So we have a warm-up here. It says, identify the pattern of these sequences of numbers. What is happening to the numbers? And it says in parentheses, plus 4 each time, multiplied by negative 3 each time, etc. So you can figure out what the patterns are for these numbers. Go ahead and pause the video. All right. So what I like to do is go step by step here and kind of figure out what's happening. Give me one sec here. So I like to go from 12 to 15. What do? Well, I add 3. How about 15 to 18? Well, I add 3. What about 18 to 21? Well, I add 3. So the pattern is consistent in all situations like this. We're going to add 3 to each number here. Okay? Next one's a little bit trickier. We have negative 4 to negative 20. How do we get from negative 4 to negative 20? Well, we could subtract 16 to get to negative 20, but if you go from negative 20 to negative 100, you can see that's not going to be minus 16. That'd be the negative 36 would be the next number. So it's probably not addition or subtraction. How about multiplication or division? Can we multiply by anything to get to negative 20? Negative 4 times what is negative 20? Well, is it positive 5 or negative 5? Remember, two negatives make a positive. So if we are, positive and negative multiplies to a negative. So we're going to have 4 times positive 5 is going to be 20. How about negative 20 times 100? That's also times 5. How about this one? Well, negative 100 times, to negative 500. Also times 5. So it looks like the rule is we're multiplying by 5 each time. All right, next one's a little trickier. How do we get from 18 to 9? Let's just try a couple things here. Well, we could subtract 9. We could also divide by 2. Let's see here. If we go from 9 to 4.5, is that subtracting 9? It is not. Looks like we're dividing by 2. Let's see if that pattern continues. Divide by 2. 9 divided by 2 is 4.5. How about this one here? That's also dividing by 2. Looks like the rule is we're going to divide by 2. So for these kind of problems, you just kind of want to try some examples and see kind of what works and make sure it's consistent across the entire set of numbers. Okay? All right, let's keep moving here. So, and these will be your answers. What's the pattern? Add 3 each time, multiply by 5 each time, divide by 2 each time. All right, here's some definitions for you. A conjecture, say conjecture, is an unproven statement that is based on observations. Based on what? Observations. But in order for it to be true, it must always be true. Must what? Always be true. Okay. All right, inductive reasoning. You may have heard of there's inductive reasoning and there's deductive reasoning. We'll talk about both of those here. So inductive reasoning is the process of finding a pattern, finding a what? A pattern for specific cases, and then writing a rule for the general case. A what? So inductive goes from specific to general. Use a specific case to write a general rule. And deductive, what do you think that's going to be? It's the opposite, which is going to be what? It's going to be a general rule to write for a specific situation. Using a general rule to write something for a specific situation. That's if you guys heard of like Sherlock Holmes uses deductive reasoning a lot. Okay. All right, a counterexample, a specific case for which the conjecture is false, which is what? It's false. And a counterexample is any example that would break the rule. Break the what? Break the rule. Okay? So if I say when you multiply two numbers, they're always negative, and I find any example that doesn't work, that would be a counterexample, and that would disprove the conjecture. That's all you need is just one example where it doesn't work, because the conjecture needs to be true, always true. Okay? All right, so we're describing a visual pattern here. We have two examples. I want you guys go ahead and see if you can sketch the next figure in the pattern for this one and checkpoint 1. Go ahead and pause the video. All right, so I kind of look from step to step here. It looks like I have a dark square, and then I have an open circle in the middle, and then I have another dark square in the middle here, and then I have another open circle. So let's go ahead and see if we can draw this here. So we're gonna have a dark square with an open circle. That's the first step, right? And it's gonna be kind of sloppy because it's kind of hard to draw in here. Then we have a dark square with an open circle. That's what we got to so far. What's gonna come next? And these are filled in here. What's going to come next? Well, we're going to have another dark square in the middle. Okay? And that's the pattern. That's very sloppy and hard to read, or hard to see, but make sure you check the notes that are posted for you if you want to see what it looks a little bit better. But basically the circles are open and the squares are dark, and so then we would just add another dark square in the middle of this right here. Okay? All right, checkpoint 1. It looks like, so we go from 2 to 4 to 6. Looks like we're adding 2 boxes every time, right? We're adding 2 boxes every time. So we were at 6, now we're at 8. And it looks like the lower box was highlighted in the lower left, then the lower left. So which box is going to be highlighted over here? The lower left. And that's kind of the pattern. All right, sounds good. Example 2. Describe, get a different color pen here. All right, describe a pattern in the numbers 1, 2.5, 4, 5.5, and write the next number in the pattern. And the same thing is for checkpoint 2. Let's get some more practice with that. We'll see if you guys can figure these out. What's the next, what's the rule, or what's the pattern, and what is the next number in the pattern? See if you can figure these out. All right, so to get from 1 to 2.5, I can either, it looks like, add 1.5, or I can multiply by 2.5. If I have to go from 2.5 to 4, I can also add 1.5. And 4 to 5.5, I can also add 1.5. So it looks like the rule is add 1.5. What would the next answer be? What would the next answer be? Looks like it would be 5.5 plus 1.5, which would be 7. So that's our answer for this one. Okay? So use addition, subtraction, multiplication, or division, and try to figure out what the next rule is. Okay? All right, how about checkpoint 2? From -1 to -4. We can either subtract 3. If we subtract 3 from here to here, that's not going to work. So we could also multiply by 4. If we multiply this side by 4, that's also going to work. So it looks like multiplying by 4 is the pattern. And what's -64 times 4? Well, that is -256. And that's the rule and the answer. All right, sounds good. Example 3 is a little bit tricky, so make sure you guys are staying with me here, okay? Let's get into it. So it says, given 5 non-collinear points, make a conjecture about the number of ways to connect different pairs of the points. What does non-collinear mean? Does that mean that they're in a straight line or not in a straight line? They are not in a straight line. So we're going to do 1, 2, we're going to just start with up to 5 non-collinear points. It helps to draw the points into the shape of like a regular polygon, okay? So I'll show you what that means here. So we have 1 point here, right? How many ways can we connect 1 point? Well, 0, right? We can't connect a point to itself. That's not going to work. 2 points. I'm going to just draw 2 points side by side here. How many ways can we connect these 2 points? Well, just once. You could, like, may think the different. If you connect it once, that's it. That's all you can do. You're not going to go, like, around. There's lots of different lines you can draw, but we're doing, like, a straight line from 1 point to the next, okay? So that's 1 connection. Now, the 3, I'm going to draw it like a triangle, okay? I'm going to draw it like a equilateral triangle. How many ways can we connect these 2 points? Well, I can connect this point to that point, and to that point, and to that point. Looks like we have 3. Now I'm going to draw a square. So you notice over here, I forgot to mention, we connect this point to these 2, and we connect this point to these 2, and those are all the different connections we can do. Basically, we're trying to connect all the non-collinear points. We're trying to connect them once and see how that works. So how can we connect the square here? Well, we can connect around the outside from there to there, there to there, there to there, and we can make a square, but there's a couple more we can do here. Do you see what they are? We're missing a couple points we can connect. We can also connect the diagonals like this, okay? To connect to different pairs of points. How many connections is that? Well, all around the outside is 4, then we have 2 in the middle, that's going to be 6. So we have 6 connections there. Now the 5 one, we're gonna draw like a pentagon, okay? Draw it kind of like a pentagon. Kind of hard to do, but draw it like a pentagon. Okay, we're trying to see how many ways we can connect points, connect different points here. So let's start here. We're going to connect, I'm going to use different colors here. We're going to go red first. I'm going to go 1, 2, let's see here. So, yeah, so we're connecting different pairs of points. So let's just do, we can do the outside, right? Let's do the outside. Okay, we connect all the outside. No, I'm trying to think of the best way to do this. Okay, we're going to connect 1 point to all the points we can connect here. So I can connect this point to that point, this point to that point, and this point to that point. Let's go around the circle now. Maybe that'll be a little bit better. Then down here, we can connect, this point's not connected, that point's not connected, and that point's not connected. So that's 6 points so far. Then we can connect this point over here, and over here, and over here. Then the last point, the last one we're missing is actually right here. So how many ways do we connect those points? So that's probably the best way to do it, is to connect, take 1 point and connect to all the points that you can, and that'll like kind of make a shape for you, okay? This should have been 10 connections, okay? So yeah, so basically we're trying to see how many ways we can connect different pairs of points. So as long as every pair is connected, then you're good. So let's figure out the pattern here. So the pattern's a little bit different. So from here to here, how do we go from 0 to 1? Well, you add 1. How do we go from 1 to 3? Well, we can multiply by 3, or we can add 2. Let's try to add 2. How do we go from 3 to 6? We add 3. How do we go from 6 to 10? Add 4. So if we're doing 6 non-collinear points, what would the pattern be? And how many ways connections would it be? Well, we do plus what? Plus 5. And then how many connections would that be? What's 10 plus 5? That is 15. So down here, it says how many connections would be made if you were to connect different pairs of 6 non-collinear points. And that would be 10 plus 5, which equals 15 connections. Okay? So I went through that kind of quick. But yeah, basically, all we're doing is connecting points. And you want to I would just start with 1 point and kind of go all the way across. Let me redo number 4 here just to show you. So if we start at this point right here, I can connect here, here, and here. These are all the different points. And if I start with this point down here, I can connect here and here. And then this point down here, I can connect here. And that's it. And that would be 1, 2, 3, 4, 5, 6. And so we have the blue lines and the green lines and the magenta line. We have 6 connections here. So basically we're trying to connect all the different points at least once. Exactly once, actually. Okay? All right, so make and test a conjecture now. So we're trying to make a rule. We're trying to make a rule and test it. So it says numbers 1, 3, and 5 are called consecutive odd numbers. Make and test a conjecture about the sum of any 3 non-consecutive numbers. Okay, so let's just pick some non-consecutive consecutive odd numbers, and we're going to, what does sum mean? What does sum mean? Sum is that addition, subtraction, multiplication, or division. That is addition, okay? The sum is addition. So consecutive odd numbers means they're basically in a row, but there's even numbers between that we're going to skip, okay? So let's just add some. Let's add them and see what we get here. So we have 1 plus 3 plus 5. What's 1 plus 3 plus 5? That is 9, okay? So this is both an odd number and it's positive. Okay, we're trying to look for characteristics here. Let's do 5 plus 7 plus 9, which are all consecutive odd numbers here. We also have, now we have 21. That is also, looks like it's odd and it's positive. Let's do some negative numbers now. Let's do negative 3 plus negative 5 plus negative 7. These are also consecutive odd numbers. That's negative 15, okay? That's not positive anymore, but it's also odd. You can see it's still an odd number, right? So what's the rule we're going to come up with here? Well, what I think it's going to be is the sum will be odd. The sum will be odd, okay? Let's test let's test one more time here. We're going to test like around 0 here. Let's do negative 3 plus negative 1 plus 1. That's kind of including negative and positive numbers. Let's see how that works. What's negative 3 plus negative 1? That's negative 4. Negative 4 plus 1 is negative 3. So this is an odd number still. So it looks like our rule does work. Okay? So these are odd numbers. Okay? Put all odd numbers. Okay? All right. Now, let's try checkpoint 4. You guys will try this one on your own. So we're make and test a conjecture about the sign of the product of any 4 negative numbers. So product mean that is what? That's multiplication. So we're multiplying any four negative numbers. We're trying to figure out what the rule is going to be, okay? So let's pick up any random negative number. Actually, why don't you guys try this? Pick any four negative numbers and try to see what kind of answer you're going to get. Is it going to be positive? Is it going to be negative? Is it going to be zero? Is it going to be odd? Is it going to be even? See if you can come up with a rule for what you think the rule is, the conjecture for this is. Go ahead. All right, we're going to pick some random numbers. We have -1. We have -2. We have -5. And we have -3. Okay. And it looks like that equals 30. So that is both positive and even. So it's positive and even right now. Let's try some other numbers here. I'm going to make these up. Let's try -3, -7, -9, and -1. Let's try this. Let's try this. So 7 times -9 times -1. So this is positive 189. So that's both positive. Is this even or odd? Oh, we got an odd result here, okay? So it looks like, what do you think the rule is? So even an odd doesn't work. We can't use this because they're different numbers here. But they're both what kind of numbers? They're both positive, so we think it should be a positive result, okay? They're both a positive result. And why is that? Can you guys see why that would be? Well, look, if we multiply these two negatives, it makes a what? It makes a positive. If we multiply these two negatives here, it's going to make a what? It's going to make a positive. So that's why it's going to be a positive result, is that multiplying an even number of positives or negatives is going to make a positive number because they're going to cancel out. Okay? All right, last thing we're going to talk about. This is actually, this is pretty cool and pretty easy, okay? It says, number 5, finding a counterexample. Find a counterexample to show the following conjecture is false, okay? To show the following conjecture is false. Okay? So, let's see here. The conjecture is the quotient of two numbers is always smaller than the dividend. Okay? So a couple things. I'm just going to do 150 over 5. Okay? This is the dividend. This is the dividend. We don't talk about this very much. And this is the divisor. Okay, so what you're dividing is the dividend, and what you're dividing by is the divisor. Okay? The quotient is the answer of a division problem. Okay, the answer of a division problem is a quotient. So it says the quotient of two numbers is always smaller than the original number. The quotient of two numbers is always the way dividing two numbers is always smaller than the original number you're dividing. Okay? Well, so the hint is to prove a conjecture false, you just need one example where it is not true. So we need to find an example where this thing is false. So if we can find one example where the answer when you divide two numbers is larger than the original number, then that would work. Okay, so let's try some numbers here. Let's try what's 4 divided by 2? That is 2. Well, 2 is less than 4, so this doesn't work. Okay, this doesn't work. So what can we do to write an example that's going to make the number on top smaller than this number here? Okay, what can we do here? Well, let's try 1 divided by 2. What's 1 divided by 2? Well, that's 0.5. Is 0.5 greater than 1? Or let's see here. Give me 1 sec. Okay, so actually, 0.5 is still less than 1, so this one also doesn't work. So how can we get creative here so that the answer is actually bigger than the answer is actually bigger than the original number we're dividing by? Well, let's try. What if we do -6 divided by -3? How would that work? What's -6 divided by -3? Well, that's 2. Is 2 greater than -6? It is. So this would be the counter example. It says any two numbers, okay? The quotient of two numbers. Doesn't say what kind of numbers. Any two numbers is always smaller. This should always be smaller than this. Is that the case right here or no? Or is 2 bigger than -6? So a counter example will be -6 divided by -3. This is a counter example. Okay? So that means the conjecture, we need to refine it or kind of adjust it because it's not always true, and a conjecture needs to always be true. Okay? So in this case, 2 is greater than, our answer is greater than the original number that we're dividing by, which is -6. And so that would be an example. Let me fix this here. So this is a counterexample, which means our conjecture is not true. We need to fix it. Okay, we have a different example here. We have find a counterexample that disproves the following conjecture. The difference of any two numbers is always smaller than the larger number. Okay, so why don't you guys try to figure this out. What does difference mean? What operation is that? That's subtraction, okay? So try to find, all you gotta do is find a single example where the resulting number is bigger than the larger number, because we're trying to find like an opposite, something that's not going to work here, okay? It's a little tricky, but basically we're trying to disprove this here. So you're trying to be contrarian. You're trying to find an example that doesn't work, okay? So use positive, use negatives, use fractions, whatever you want to do. Give it a try. See if you can figure this out. All right, difference of any two numbers is always smaller than the larger number. Let's just do 7 minus 2. What is that? Well, that's 5. So 5 is also, this is smaller. So 5 is smaller than 7, than the larger number. So this one doesn't work. We can't do that. What if we subtract a bigger number from a smaller number? What if we do 5 minus 8? What's that? Well, that equals -3. Is -3 larger than the larger number? -3 is still smaller than 5, so that's not going to work either. Okay, what if we subtract a negative? What if we do 4 minus -6? What does that equal to? Well, that's equal to 10. Is 10 bigger than the bigger number, which is 4? It is. So our example would be, our counterexample would be this. This would be our counterexample, okay? Because it's an example that proves the conjecture false. It's just any example. Like, if you come up with a rule, there's a rule, and you find one example that doesn't work, then the rule is false. You have to fix the rule, okay? That's all we're doing for these problems here. I hope that makes sense. This is kind of tricky each year for students, but you're just trying to find, so if you say, like, let's see here. All people who like Harry Potter fans are cool. I mean, that's the rule. If you can find one example where you find a person who likes Harry Potter who's not cool, then that would disprove the rule. And that's kind of what we're doing here, okay? I hope that makes sense. Thank you guys for watching. Have a great day, and we will talk soon.